All right, line A4, learning task 6, we're going to describe parallel RC circuits. So anytime we got a C inside of the title, it means that we are looking at circuits that contain some capacitance. In a lot of ways, capacitance is a lot easier to go and deal with than inductance because capacitance is not going to go and have any watts to it, right? A capacitor is going to have a dielectric or an insulation between it, so there should be no current that is going to travel through. Therefore, we should never have anything like on our inductive circuits where we have got that practical inductor, right? The component that is going to be made up of both resistance and inductance. As soon as we're working inside of capacitance, we don't have to worry about that, which means that this branch here gets termed as being just strictly capacitive. It's going to go and dissipate only VARs, and it isn't going to go and have an impedance. It's only going to go and have an XC to it. Makes all of our addition of values much, much easier. Once again, as this thing is going to go and be a parallel circuit, our constant for the circuit is going to be voltage. That voltage is going to equal this voltage, which is going to go and equal this voltage that we will have across each one of these. And we're going to go and use a lot of the E squared over top of our formula to go and convert everything into power. Once again, because power is going to be our friendliest value to go and work with. Power does not lie, so let's go and work with it where we can. We've got our line voltage, really easy to use, E squared over top of my R. That's going to go and give me watts for this branch over here. And if I do E squared over top of my capacitive reactance over here, that's going to go and give me my VARs that I would go and have off of that branch over there. Once again, once we have it transferred into watts and VARs, we're going to be able to go and add those together. VARs are going to go downward for a capacitor. We'll take a look at that in a minute. But we're going to be able to go and figure out total amounts of VA that we would have off of each of these circuits. Current for these is going to be added up through Kirchhoff's current law. Our currents are going to be operating at different angles. We know any resistive current is going to be at an angle of 0. Anything that's going to be at a capacitive current is going to be ice, right? It's going to be leading our voltage by 90 degrees. And because voltage is our reference, that means that my IC, my current from my capacitor, has to be up there so that it's going to be leading. So we would say that this is going to be at a positive 90 degrees that we are going to go and have any sort of values that we'll utilize off of there. Once again, as soon as we can go and figure out our angles, we can go and use our sharp calculator to go and punch those values in together. Add them up vectorially so that we are ready to go. Triangles that we can utilize for this, primarily, if we're going to go and use a triangle, we're going to try to go to our power triangle. However, we do have the option of also using our current triangle. That's what they're showing over here. My IC, which is going upwards because it's leading. My IR, which is going to be in phase with my voltage because it's my resistance and voltage are going to be in phase. We can't use this one. We can also go and use one of those inverted impedance triangles. But an inverted impedance triangle is always going to be more difficult to work with than working off of our power or off of our current. Once again, as I said before in learning task number 5, I am never going to go and create a test question that can only be solved off of the impedance triangle, a parallel impedance triangle. You might be able to use one if you're comfortable with them, but you will never be required to go and deal with one. I don't think there's any exams anywhere, standard level exams, interprovincial, any of those big exams that you're going to be hitting where you're only going to be stuck to that. That would be crazy if anybody designed it. I don't know because I don't get to go and design them all. But for the most part, what we're trying to train is practical electricians. So don't stress about that inverted impedance one. We will deal with a couple of calculations to show how they're done later on, but we're mostly going to stay far away from it. If we know what we have got for our currents, like this, our resistive current, our capacitive current, we can go and establish a total current. Once we've got a total current, we can go and get that phase angle. As always, when we're dealing with RL and C types of circuits, once we know the phase angle, we can then calculate our power factor off of that by just taking the cosine of that angle. All right, that is really all we have to cover off of these ones. They're far simpler because we don't have any sort of practical capacitance. Capacitance is just going to be straight up XC and VARs because there should be no current flow through them and therefore no watts off of them. We'll practice all of our calculations later on once we get into the full RLC circuits.